Kinetic energy is the energy of motion. It can be directly calculated by multiplying half of the mass by the square of the velocity, or indirectly calculated by using the law of conservation of energy. Since the law of conservation of energy states that energy is not created or destroyed, if we hold an object still and drop it, we can assume the kinetic energy when it reaches the floor will be equal to the gravitational potential energy that it possessed before we dropped it. By extension, if we can calculate gravitational potential energy by multiplying the height with the gravitational acceleration of the Earth, and then multiplying that by the mass, we can indirectly calculate potential energy. This is the essence of the experiment we performed. By using these principles, we can calculate the final kinetic energy both directly and indirectly. We performed 3 trials. In each, we dropped a 532-gram basketball from a height of 2.2 meters. We then used the online video analysis software JSTrack to plot the ball's position over time. From the values gathered, we could then find the final velocity, which, when plugged into the 1/2 times mass times velocity squared formula, yields the final kinetic energy of the ball. Performing this operation on our trials with our gathered final velocity and a mass of 0.532 kilograms, then averaging the results, yields a directly calculated kinetic energy of 10.8 joules. We can find the indirect kinetic energy by multiplying the mass of 0.532 kilograms by the gravitational acceleration of 9.8 meters per second squared by the height of 2.2 meters. This yields us an indirectly calculated final kinetic energy of 11.5 joules. For the ELA component of our project, we wrote a diary. For the first week, we familiarized ourselves with the experiment. We read up on projects and looked back on previous labs and experiments that were similar. By the end of the week, we knew what to do and how to do it. We needed to find the software for our project. In the second week, we began by deciding on the procedure for our experiment. We found out what software we needed to use, and then we watched guides on how to use it. In the end, we decided on Pasco Capstone software in order to record the values. The third week was spent recording the videos for the ball drop experiment. We dropped the ball in front of a meter stick so we could align the real-world measurements in the software. Next, we sent all of the videos to our laptops and computers via email so we could use them inside the software. We uploaded our videos to Pasco Capstone and measured our needed values so that we could do our calculations. We also worked on our website and finished a good portion of our PBL website. In the fifth week, we did all of our calculations of averages, confidence intervals, and statistics and uploaded them to the PBL website. The final week, we finished up final touches on the website, including decorations, as well as the social studies component. For our social studies component, we researched the conservation of energy. The conservation of energy is a principle of physics which states that the energy of a closed system remains constant. This can be observed in particle collisions, namely elastic collisions, where the sum of kinetic energy of the particles before and after the collision is the same. The notion of energy was further extended to include other forms, such as potential and thermal energy. For example, when a pendulum swings upward, its kinetic energy is converted to potential energy, and when it swings back down, the potential energy is converted back into kinetic energy. Friction, however, dissipates energy gradually out of the system. This led to the concept of energy being included heat generated by friction. Ultimately, it was concluded that the sum of kinetic, potential, and thermal energy is what is conserved, not just kinetic or potential energy. This is the essence of the first law of thermodynamics. Additionally, energy can take many other forms, such as electric currents, electric and magnetic fields, and energy stored in fuels and chemicals. For example, when a car moves, the chemical energy in its gasoline is converted into the kinetic energy of motion. You may notice the disconnect between indirectly and directly calculated kinetic energies, which seems contrary to the conservation of momentum. This could be due to a variety of reasons, namely some energy being lost to air resistance, errors in the JSTrack software, or even human error in dropping the ball at the exact height. In conclusion, The values of directly and indirectly calculated kinetic energies are close enough to prove conservation of energy.